Hi, my name is Xiao and I will be presenting Why You Think is Why You Retrieve, a user intent-aware framework with multi-modal inputs for visualization retrieval. And there are enormous charts flourishing on the internet. To retrieve and find a specific type of visualization from large dataset is very important. The mainstream query for retrieval can either be grammar configuration, chart reference, or natural language. Also, it is fundamental for some downstream tasks, such as recommendation system or creating a chart collections. From the query to the result, many problems may occur in the retrieval process. Different users will have different intents. In this case, the query charts features four main attributes. For the first intent, the user wants to delete some of the origin attributes of the query charts. For the second intent, the user wants to change the origin attributes from the increased trend to the decreased trend. For the third intent, the user wants to add a novel attributes like 3D style beyond the query chart. So as you can see, the slightly change in the user's intent will result in different intent attributes. So we should take the intent into consideration for designing the retrieval framework. However, previous work usually ignores the importance of intent, which can be mainly categorized into example-based and definition-based retrieval. Example-based retrieval aims to delineate the similarity between the query charts and the retrieval result from database. It scans all the low-level visual features of the query charts and treat with the attributes indiscriminately. Finally, it will return some result that similar to the query charts. So you can see the result attributes are nearly equal to the query attributes. For the definition-based retrieval, the result attributes strongly rely on the predefined attributes. In this work, we propose What You Think is Why You Retrieve framework. It combines the advantages of both example-based retrieval in terms of its high capability of capturing implicit features and also definition-based retrieval because of its high interpretability of explicit attributes. Besides, we integrate multi-modal input as intent prompt, which allows users to use natural language to represent their intents. To explore what users care about when they use chart retrieval, we conduct a preliminary study. The chart in the left indicates that the type, color, trend, and layout were mostly and frequently mentioned by the participants and can be applied to different types of charts. And the form, background, context were mentioned less than the primary attributes. We dubbed them as the extended attributes. So the all attributes of a chart can be represented by this doublet consisting of both primary and extended attributes. The illustration in the right shows that different attribute options of different types of charts. Our proposed pipeline consists of two essential stages. The annotation stage disentangles attributes and enables a flexible combination of these attributes. The retrieval stage digests the multi-modal inputs to get the target's retrieval results. In the annotation stage, we input a query chart and leverage several classifiers to extract the attributes. Then the user can flexibly select and combine the attributes as they need to construct the final intent attributes. In the retrieval stage, there are two paths together to obtain the target's retrieval results. In the first path, it uses the intent attributes as condition to guide the filtering process. In the second path, it leverages the multi-modality encoder to deal with the chart image and user intent prompt to obtain the query feature. Then the similarity will be conducted between the query feature and candidate features. Throughout the pipeline, users' intents can be injected in three ways. Firstly, classifier customization. User can tailor the usage of classifiers depending on their needs. Secondly, user can flexibly select and combine the attributes and their needs. Thirdly, user can customize the prompt to represent their actual intent. In the annotation stage, we leverage several classifiers to extract the attributes of the query chart. For the primary attributes, we utilize the resonate architecture as a backbone. The only difference in the four classifiers is the number of output channels in the last fully connection layers. To tackle the problem of imbalanced and hard samples, we use focal loss in the training process. For the extended attributes, we input the user-defined labels and the query chart, and then project this input into clip model's multi-modality embedding space. In this space, the chart will be pushed to the location that's close to the corresponding attributes. So finally, we will get the attributes with the highest probability. In the retrieval stage, the first pass is called intent-aware filter. The intent attributes from the annotation stage will guide this filtering process. In the second pass, the multi-modal encoder will digest both query charts and the text prompt from the users to obtain the multi-modal query feature. At the core of the retrieval, similarity modeling will be performed with the triplets. The first is the global perception score, which aims to estimate the similarity score between the query chart and the candidate. The second score is in terms of the intent attribute similarity. The third is the feature matching score, which aims to compare the similarity between the multimodal features and the candidate features. Specifically, intent attribute score and the feature matching score jointly contribute to the exponential term of the similarity modeling. The global perception score serves as a coefficient for this equation. The gamma and mu are the two hyperparameters controlling the intent attribute score and the feature matching score, which can be tuned for the better retrieval results. In this work, we utilized the BIGO dataset. To make our framework more robust, we further add some difficult instances by collecting the images from the internet, which supplements a large number of the stylized and irregular charts. As the table shows, we finally get a dataset with 18 types, 33,260 charts in total. The number of the charts in different types are very unbalanced. Then we take the evaluation for annotation and retrieval respectively. For annotation, we evaluate its performance with different losses. The methods with focal loss will get better results. For the retrieval without intent, we use the F1 score as metric. We use two methods as a counterpart, a conventional method hog algorithm and a CNN-based method. In this table, we can see our methods outperforms other two methods. Moreover, as the K increases, our methods can keep a relatively stable performance, while others too drop dramatically. For the retrieval with intent, the other two methods still struggle to find the examples and similar to the query charts. In contrary, our methods focus on the user's intent. If user wants to retrieve some images similar to the query chart but with vertical layout, our system will help them to find more targeted results. We also design an interface for this prototype system, which consists of three main views. The annotation view will tell the user result of primary attributes of the query chart. The retrieval view allows users to add the extended attributes as well as allows them to flexibly select and combine the intent attributes. Finally, the retrieved charts will shown in the result view. In the case study, we mainly focus on two usage scenarios. Firstly is a design space extension by explicit goals. There are 3 main operations and 1 application. The first rule is general intent-free retrieval. Following rule is intent-aware retrieval. In terms of original attribute change, we can get several box plots with vertical layout, in spite of the query chart is in horizontal layout. Similarly, we can turn the color of the map from blue to pink. It's worth to note that the retrieved result with the lower mu will be more similar to the query chart. So there will be a trade-off between the query chart and the user's intent. For the existing attribute deletion, we can remove the dark background of the donut chart by adding the extended attribute. Also, we can represent our intent using the text prompt. In this case, we add the text prompt without numbers. So the retrieved results are the heat maps without numbers in the unit squares. For the new attribute additions, we can get some histograms with curve to indicate the distribution, even though the query chart has no curve on it. Similarly, we can get some box plots with dots, even though the query chart has no dots on it. In the end, we show the interesting application, attribute transfer, which combines several operations before. Giving a circular pancake chart with multiple circles in different scales, we need a heat map. So the system will return some heat map with the shape encoding and circle. Moreover, we can transfer the color from the timeline to the bar chart or the circular pancake chart. For the another usage scenarios, fuzzy retrieval by user intent, we use 3 cases for illustration. Firstly, the information seeking. Giving a query chart and the keywords life expectancy, we can get several similar scatter plots with the words life expectancy on it. Secondly, the relevant topic finding. We can retrieve word clouds about the technology topic, or even the word cloud with the shape of tree. Moreover, the system supports abstract description searching. Giving a simple timeline, we can get the result with more fancy style. Also, we can narrow down the searching scope by adding a new attribute, horizontal layout. Or we can say the retrieved result should be more suitable for exhibiting in slides, so the retrieved diagram will be more visually pleasant. To fully evaluate the performance of our proposed method, we conduct a user interview, which entails 7 participants, 4 experts and 3 novices. For introducing their background, we inform them of the usage scenarios of chart retrieval, instruct them to familiar with the system workflow, and show some examples of prompt. In the explore stage, we allow the users to freely explore and use our system. Finally, we conduct an interview about the usability of our system. During the interview, most participants gave us the positive feedbacks. They said it is effective because the retrieved results can be consistent with their intent. Also, they said it is efficient to save the time of checking a lot of examples. Finally, they felt satisfied because this system can inspire them to come up with new ideas as well as validate ideas quickly. Also, they point out some limitations for our proposed system. Firstly, how to deal with the trade-off between the query chart and user's intent. Secondly, prompt sensibility. As it's shown in the right, different prompts can result in varying outcomes. It is not supported well for visualization professional expression, such as encoding. Thirdly, the model's effectiveness. Not all the retrieved results can be consistent with user's intent. So the alignment between the text and the visual feature of clip model still needs improvement. In summary, our contribution include a novel framework integrating user intent into chart retrieval process, and implementation of a prototype system combining clip model with visual interface. The dataset, code, pre-trained model are released at this link. You can try it out. Thank you for listening.